Hi, my name is Griffin Price, and this is Lab 3. To introduce this lab, the purpose of it is to find the mass of a black hole given a star's motion, and to also find the initial velocity of a spaceship that will let it avoid crashing into a black hole. And those are some preview of my final results that I'll explain later. So some fundamental principles to go through. Obviously, net force is equal to dp over dt, which is also equal to the mass times delta v over delta t, which is equal to mass times acceleration. The net force is equal to the parallel and perpendicular components of that net force added together. And then we have some update formulas. We have the velocity update formula and the position update formula that can be derived from Newton's second law. And since we're dealing with celestial bodies in this lab, the main force at play is going to be gravitational force, which the equation is given right there. And since the gravity in this case is non-constant, the average velocity is going to be approximately the final velocity. So part one, we're going to find the mass of a black hole. Our system is the black hole. The surroundings of the system is going to be the star that affects it. And some initial conditions that were given is that the change in time is 1 day, but since we're dealing seconds, we have to do 86,400 seconds. And we're given that the mass of the star is 2 times 10 to the 30 kilograms. So our coding for part one, basically, the first thing I did was I found momentum, right? And then I used momentum to find the change of momentum. I used that to find dp over dt, which is obviously equal to net force. And then I used dp over dt to also, and the momentum to also find the parallel and perpendicular components of dp dt, which is equal to the parallel and perpendicular components of net force. And the code on the right there is just to help map out the arrows and let you get a good look at the parallel and perpendicular components. So obviously, these are my results, that the average mass of a black hole is 1.2410 times 10 to the 34 kilograms, which I got by taking the average of 509 entries I got from the code for the mass of the black hole. And I have the net force and its parallel and perpendicular components. And as you can see, there's the arrows that accurately map out the parallel and perpendicular components along as the net force. Part two of this lab, the system of it is the rocket. The surroundings is going to be the black hole and the planet, and some initial conditions were given is the mass of the black hole, which we found in part one, and the change in time is now 1 second rather than 1 day. So coding for part two, basically, I wanted to find the velocity and position of the planet and the ship, because the whole purpose of part two is that we're trying to get the ship, we're trying to return home. So we want to escape the planet's gravity as long as escape the black hole's gravity and get out. So what I did first was I used the gravitational equation to find the force, all the forces on the planet, all the net forces on the planet, so from the black hole and the ship. And then I used the gravitational equations to find all the forces on the ship from the black hole and the planet. And then I used those along with some update formulas to find the velocity and positions of the planet and the ship. And the results I got was that the rocket's initial velocity to escape the planet and the black hole was that it needed to have negative 3.45 times 10 to the 7 meters per second in the x direction and 2.98 times 10 to the 6 meters per second in the y direction to do this. So some sources for error. In part one, I calculated 509 the code calculated 509 entries, which I took the average of. So obviously if I had more entries, I feel like the average would probably be a little bit more accurate. And for part two, the initial velocity that I used was just plugging in, I just plugged in numbers until something worked. But I will say that I did do this for a considerable amount of time, and I tried to get as close to the black hole as possible to get the best numbers, the lowest numbers. But obviously there probably is a set of numbers that is more accurate than the ones I used. So what does it mean? The difference between net force and change of momentum, there's not much. Mathematically, they're equivalent. But I will say that the parallel and perpendicular forces of the momentum are much easier to calculate since you only need mass, change in velocity, and change in time. Now, what if you wanted the rocket to orbit the black hole but escape the planet? Well, obviously you would need enough velocity to escape the planet's gravity, but your velocity of the rocket would need to be equal to the gravity of the planet, since you want to remain in orbit. Considerably the x-coordinate, since your y-coordinate is going to be the planet's gravity because it's going to be pulling the rocket down, but you want your x-coordinate to also be equal to the black hole's gravity, so it will fall in the other direction and never even crash into the black hole. Thank you for your time.